a glimpse into the past, from viscometers to nanotechnology. We humans have always been fascinated by the properties of matter. How thick is a liquid? How easily does it flow? These questions led to the invention of remarkable tools. In the 19th century, Friedrich Wilhelm Ostwald developed the viscometer. It measures a fluid's resistance to flow, its viscosity. Around the same time, Isidor Traub invented the tensiometer. It measures surface tension, the force that makes liquids behave like stretched elastic sheets. These inventions were groundbreaking. They opened up new avenues in understanding the physical world around us. We could now quantify the properties of liquids with precision. This knowledge proved invaluable in fields like chemistry, physics, and engineering. But as we delved deeper into the microscopic world, new challenges arose. We needed to understand forces at the molecular level. This is where nanotechnology comes in. Nanotechnology deals with manipulating matter at the atomic and molecular scale. It's like having tiny building blocks 1 billion times smaller than a meter. With nanotechnology, we can isolate individual molecules. We can study their properties and interactions like never before. This has led to incredible breakthroughs in materials, science, medicine, and beyond. The challenge of tiny forces, why we need new tools. Imagine trying to measure the weight of a feather with a bathroom scale. It wouldn't be easy, right? The scale is simply not sensitive enough to detect such small changes. The same principle applies to measuring forces at the nanoscale. Traditional tools like viscometers and tensiometers, though ingenious, are not designed for this level of precision. They are like the bathroom scale trying to weigh a feather. We need new tools that can operate in the realm of atoms and molecules. This is where the concepts of potential and kinetic energy come into play. At the macroscopic level, we can easily observe these forms of energy. Think of a roller coaster at the top of a hill, potential energy, and then racing down the track, kinetic energy. However, at the nanoscale, these energy forms become intertwined and difficult to separate. This poses a significant challenge in understanding and manipulating forces at this level. We need a way to untangle these forces, to measure them individually and understand their interplay. Nanoscience isolating molecules and building new materials. Imagine a world where we can manipulate individual molecules like Lego blocks. That's the promise of nanoscience. It's a realm where the impossible becomes possible. With nanoscience, we can isolate single molecules. We can study their unique properties and understand how they interact with each other. Think of a water molecule, H2O. It's incredibly small, but it has remarkable properties. It's polar, meaning it has a positive and negative end. This polarity allows water molecules to stick together, forming the life-giving liquid we depend on. Nanoscience allows us to study these interactions in detail. We can see how molecules attract or repel each other. We can even manipulate these forces to create new materials with unique properties. One such property is monolayer adhesion. It's the force that holds a single layer of molecules together. This is crucial in nanoformulations, where we're dealing with materials just a few atoms thick. The magic of adhesion, transforming cohesion for nanoformulations. In the nanoscopic world, forces behave differently. Cohesion, the force that holds molecules of the same substance together, plays a crucial role. It's what gives a water droplet its shape. But for nanoformulations, we need to go beyond cohesion. We need adhesion, the force that makes different substances stick together. Think of glue. It's an adhesive that can bond different materials together. In nanoformulations, we need to achieve similar adhesion at the molecular level. This is where the magic happens. By understanding and manipulating cohesive forces, we can transform them into adhesive forces. It's like turning water into glue. This transformation is key to creating stable and effective nanoformulations. Oil and water don't mix. A tale of unshared cohesive forces. We've all seen it. Oil and water just don't mix. You can shake them together, but they always separate. This simple observation reveals a fundamental principle of chemistry: unshared cohesive forces. Water molecules are polar, meaning they have positive and negative ends. They love to stick together, forming strong cohesive bonds. Oil molecules, on the other hand, are non-polar. They have no positive or negative ends. Because of these differences, water and oil molecules don't share cohesive forces. They can't form strong bonds with each other. It's like trying to fit square pegs into round holes. It just doesn't work. This principle is crucial in nanoformulations. We need to carefully consider the cohesive forces of different substances. We need to find ways to overcome unshared cohesive forces to create stable mixtures. Introducing the Survismeter, a new era in measuring viscosity and surface tension. Remember the viscometer and tensiometer we talked about earlier? They were groundbreaking inventions, but they have limitations in the nano world. That's where the Survismeter comes in. The Survismeter is a revolutionary tool that combines the best of both worlds. It measures both viscosity and surface tension, but with nanoscale precision. It's like having a microscope and a telescope in one. How does it work? The Survismeter measures two key parameters: viscous flow time and pendant drop numbers. Viscous flow time tells us how long it takes for a liquid to flow through a narrow capillary. Pendant drop numbers measure the number of droplets that form from a hanging liquid before it detaches. By analyzing these parameters, we can accurately determine both viscosity and surface tension, even for tiny amounts of liquids.